So really, this is the notation that we gave at the beginning of this chapter. So let's recall the following. Delta f sub a at h is df sub a at h plus little o of h. So let's rewrite it. If my function goes from the reals to the reals, then I can rewrite this in standard sort of notation. Delta, the change in f, is f of a plus h minus f of a. And this is what's called the, well, differential notation. So is equal to f prime at a times h plus this little o of h. So let h equal x minus a. Then I can rewrite a plus h. Well, a's cancel. So this just becomes x. And so I have that this can be written as f of a minus, start all over again, as f of x minus f of a equals f prime at a times x minus a times little o of x minus a. Let's bring this to the other side of my equation. So f of x is equal to f of a plus f prime at a times x minus a times this little o of x minus a. And so in your book, they write, instead of writing a little o notation, they write these little squiggly lines. And this little squiggly line means, well, it's this side, this left-hand side is approximately equal to the right-hand side plus an error. And so they just don't write the error. So f of x is approximately equal to f of a plus f prime at a times x minus a. And this is the notation in the book. So the tangent line approximation. The tangent line approximation to f at a is exactly what we wrote. F of x is approximately equal to f of a plus f prime at a times x minus a. Now, horrible terminology, but everyone uses it. I use the terminology, which is the linearization of the function f at a. It actually isn't linearization. So we actually haven't linearized. We've made it into an affine approximation. So it's supposed to be called the affinization, but I can't pronounce that. And so who pronounces affinization? Who says that? So we just say linearization, even though we know it's not really linearizing. We just say it anyway. And that's due to the fact that, one, everyone else says that. So everyone else is wrong, so I might as well be wrong. The book also says it, and well, everyone says it. And due to the fact that historically, this is what it's been called. So it's been called this since the beginning of time, actually just like 300 years or 400 years, the past like 300 or 400 years. But you know, if everyone calls it this, then everyone just keeps calling it that. So let L of x be defined as f of x as f at a plus f prime at a times x minus a. It's basically, they're trying to say that it's equal to this, but it's not because it includes this guy. So it's not quite a linear, this is a linearization here. If you don't include the f of a, that's a linearization. And so this here is actually a linearization. But, so it should include that, but who cares? We all call it linearization. So even though it adds this extra term here, which makes it into an affine transformation, we will say that this is the linearization of my function at A, equal to f of A plus f prime of A times x minus A. Let me give you some additional terminology. Linearization. So the infinitesimals, the increments. And so let me tell you what an increment is. So let delta x equal x1 minus x0. It's what we were calling before h. It's our little bitty p. It's our little increment that we're changing x. They used to call these infinitesimals. It's the little small thing that we're changing x by. We actually have no restriction on if delta x is big or small. Usually it's small, but there's really no restriction that it has to be small. Delta y is, well, the change in y sub 1 minus y sub 0. And so if I write it in function instead of as a y, as an f, delta f is equal to f x sub 1 minus f x sub 0. And so delta y is equal to f at x sub 0 plus delta x minus f at x sub 0. It is, in our previous notation, delta f sub x sub 0 at delta x. And so, let me give you a little picture of what we're trying to do here. So suppose I have some function, y equal f of x, relative to some coordinate system, the x and y coordinate system. Then the secant line through x0, y0, x1, y1 consists of, well, the change in x and the change here in y. The slope of a line is equal to the change in y over the change in x. So let me give you the increment definition of the derivative. If you make the change in y, the change in x go to 0, meaning that you keep getting closer and closer to x sub 0, then this slope of the secant line approaches the slope of the tangent line. So my increment definition of derivative. The derivative f prime at x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. The limit as x approaches the limit as delta x approaches 0 of delta y over delta x. It's the infinitesimal increment of y over this infinitesimal increment in x. And so it is dy over dx. And that's how they get their, Leibniz gets his notation. It's this infinitesimal change in y over this infinitesimal change in x. And so let y equal f of x, where f is a differentiable function, and let delta x be an increment in x. The differential dx of the variable x is denoted by dx, and it's just equal to delta x. The differential dy of the variable y is again denoted by dy, and it's equal to f prime of x times dx. And so if I rewrite this in Leibniz notation, this says that dy is equal to dx over dy times dx. And so that's why, quote unquote, these work, because you're canceling these infinitesimals. Of course, that's not what is really happening. That's the intuition that was given back in when they started to invent calculus in the 1600s. So, approximation formula for determining delta x. So we have here that for determining delta y. So we have here that if delta x is approximately equal to 0, then delta y is approximately equal to d of y. So we have the derivative as a quotient of differentials, that dy over dx is just dy, which is f prime of x dx over your dx. So let's talk about how to approximate. And so the linear approximation formula. Let y equal f of x with f being differentiable, and let delta x be some increment in x, then delta y is approximately dy. Therefore, the change in y is approximately dy. So f of x plus delta x minus f of x is approximately dy. So that says that you can approximate f of x plus delta x by f of x plus dy. So f of x plus delta x is approximately equal to f of x plus dy. And dy is, well, f prime at x delta x. Therefore, I can approximate f of x plus delta x using the following formula. F of x plus delta x is approximately equal to f of x plus f prime of x times delta x. Okay, so that's a nice approximation formula. It's our linearization for my function. Note, if W denotes a measurement with a maximum error of delta W, then the average error is delta W over W. The percentage error is delta W over W times 100%. So let me give you some terminology, the differential terminology, which will give you, and some formulas involving differentials. So dy equals f prime of x dx. Really just think of this as being our definition of the derivative. Then we have the following rules. So rules for the differential. Let a and b be constant. Let u and v be differentiable functions. Then the differential of a constant is just 0. we have the product rule. And so we have that the differential of AU plus BV is ADU plus BDV. We can think of these as being the sum rule and the constant multiple rule. D of U plus V is DU plus DV. D of AU is ADU. We also have the product rule. DU times V is VDU plus UDV. This will be the integration by parts. So this is actually integration by parts formula, which is the very first topic or second topic that you talk about in Math 262, your next class. Next, the quotient rule. Du divided by V is VDU minus UDV over V squared. The reciprocal rule. D1 over U is equal to negative 1 over U squared du, and the power rule. Dx to the power n is equal to n x to the power n minus 1 dx. So, and it turns out that, well, a lot of these formulas are going to be important when we start to talk about derivatives. Not about derivatives, about antiderivatives, integrals. Okay, so let's do some examples. On page 192. Problems 1 through 4, and the linearization, L of x, of the function at A. So problem number 2, f of x equals sine x, A is equal to pi over 6. So first off, the linearization of f of x at x equal A. And so L of x is equal to f of A plus f prime at A times, oh, maybe I'll call it dx. Well, no, maybe I'll call it x minus A. So in our particular case, we want to do this for f of x equaling the sine of x and A equaling pi over 6. So let's determine f at A and f prime at A. Well, f at pi over 6. Let's draw a picture. Okay, so this is sine pi over 6. Well, the sine of pi over 6 so I have to look at the sine of pi over 6. So it's 1 over 2. It's the opposite over the hypotenuse. Let's look at the derivative of the sine of x, cosine x. So let's evaluate the derivative at pi over 6. And so the cosine of pi over 6 is the adjacent over the hypotenuse, rad 3 over 2. Okay, so using that, I can figure out the linearization. All of x is equal to f at a, 1/2, plus f prime at a, rad 3 over 2, times x minus a, pi over 6. And that's your linearization. Any questions about that? Okay, let me do, in problems 23 through 28. Use a linear approximation or differentials, same thing, to estimate the given number. So problem 26, the square root of 100.5. Okay, so good. Now we're going to be using all this abstract stuff to give us a nice calculation. So it turns out that all this quote unquote abstract stuff is useful because you do it in a calculation and out pops your answer. Okay, so recall that we have the differential approximation. Oops, the differential approximation. That the change in y is approximately equal to dy. That was the big sort of quote unquote take from this section. It's really what we did in the beginning of this chapter. And so let y equal the square root of x to the 1/2. Then dy is 1/2 x to the negative 1/2 dx. And now let's approximate this. So in this case, I want to approximate the square root of 100.5. So I can write this as the square root of 100 plus 0.5. Oh, actually, I should have told you where that came from. Actually, maybe what I'll do is bring this down. What happened there? My y somehow got attached. So this up. Yeah. Get rid of that. My y somehow keep getting attached. Okay, so I have here that a should equal 100. My delta x should equal 0.5. Oops. I have here a should be 100, delta x should be 0.5. And what am I doing to this? I'm taking its square root. So I should have that my function is the square root of x. So really, that's how I got this. So that's why I sort of put it below. Okay, so there. Oh, that's nice. Okay, so my y's I keep missing them. Okay, so let's figure out what this is. So dy is equal to 1/2. Plug in A, or X, 100. And plug in delta X, dx, 0.5. And so I get that dy is equal to 1/2. The square root of 100 is 10. So 100 to the negative 1/2 is 1/10. And 0.5 is 1/2. So this is equal to 1/400. And maybe I'll write this. And so that's 25/1000. Yeah, 0.025. Okay, so since delta y is approximately dy, then I have that delta y is approximately 0.025. And so the change in y, well, maybe I'll write it this way before I do that. And so the change in y is equal to y at 100.5 minus f at 100. And so this is equal to the square root of 100.5 minus the square root of 100. So radical 100.5 minus 10. But that's equal to, approximately equal to dy, and we figured out dy. It's equal to 0.025. So we're saying that these are approximately equal. So delta y should be approximately this. So delta y should be approximately 0.025. Add 10 to both sides of your equation. So you have calculated the square root of 100.5 without using a calculator. And so notice I didn't use any calculators here. And it's actually, if you plug it onto a calculator, what you will notice is that you get a pretty good approximation. And so this is actually a good approximation without you having to rely on a calculator. Okay, so tomorrow, so I'm going to end that. I guess I'll end it today at this point and continue with this on Monday because today's Thursday. So tomorrow will be the, no, I will continue with this tomorrow. I'm sorry, I'm going to continue with this tomorrow. And I'll probably finish off this section and maybe start chapter 3 tomorrow. At, I guess, 9:30, I will stop lecturing. And then in like about 5 minutes or so after that, I will start the exam. And you have some like 2 hours or something to get it done. So actually, I think 90 minutes to complete your exam. Any questions about anything? If not, I guess I'll be letting you guys out now. Okay, so I'll see you guys tomorrow.
Have a good day, Professor.
Okay then, bye-bye now. Is there something that's near cosine of 29 degrees that I can calculate?
Well, I probably can calculate cosine of 30 degrees. So I want to use that to be able to calculate cosine of 29 degrees. Okay, so I want to use the fact that 29 can be written as 30 degrees minus 1 degree. And then use my differential approximation. Oh, and I guess I should say, and I also want to use the fact that, well, my y should be cosine of x. So let's use my differential approximation. So we have that delta y should be approximately equal to dy. And this is when, of course, we're doing that theta is very small, is very near 0. And well, it will be negative 1 degree, so it's going to be very small. And so I have that, I let y equal cosine x. So dy, well, the derivative of cosine, I should be using x's here. So the derivative of cosine is going to be a minus sine x dx. And that's your differential. And well, I will write 29 degrees as 30 degrees minus 1 degree. Now, of course, I can't use degrees. So, well, let's see. What's cosine of 30 degrees? Oh, well, maybe I'll do it this way. It's going to be pi over 6, of course. And so there are pi radians at 180 degrees. There are pi radians at 180 degrees. And so this is going to equal pi over 6. Oh, actually, I should move this also. So this is going to equal pi over 6 minus pi over 80, or 180. Okay. So this says that, I guess I'll use the notation where a. So a is pi over 6 radians, and dx is equal to a negative pi over 180. And so I have that dy is equal to a negative sine of pi over 6 times negative pi over 180. Well, let's recall oh no, actually it's if this is a 30, 60, 90 triangle, this is a 30, that's 60 degrees, that's pi over 3. And so this is pi over 6 over here. So maybe I'll write the pi over 6 here. Wait, that's the bigger angle. No, pi over 6 is the smaller one. Sorry. So dy is equal to negative sorry, I'm just trying to be sure that that's correct, that this triangle is correct. Okay, so that's 30. That's a 60. Yeah, that's the smaller one. Okay, and so it's 1/2 times the negative pi over 180. So this is equal to negative, make that a positive pi over 360. Okay. Next. We have that delta y. Well, delta y is going to be y of, let me write it as a plus h minus y of a. And then maybe I'll put it as delta x. So this is going to be y at the 30 degrees minus the 1 degree minus y at the 1 degree, which is y where we want to figure it out at 29 degrees minus, oops, minus y 30. Okay, so this is cosine of 29 degrees minus cosine of 30 degrees. Cosine of 29 degrees minus the cosine of, well, pi over 6. because we've already done that. Here, that 30 degrees is pi over 6. And so cosine of pi over 6 is rad 3 over 2. Oops. Rad 3 over 2. Now, since dy is approximately the change in x, well, we know what dy is, and we know what delta x is. And so delta y approximately equaling delta x says that the cosine of 29 degrees minus rad 3 over 2 is approximately equal to pi over 360. And so now we can figure out what cosine of 29 degrees is. So cosine of 29 degrees is approximately equal to rad 3 over 2 plus pi over 360. And that's your answer. Now, unfortunately, I guess you have to plug it. Well, you could calculate this without that. But so there are ways to compute the square root without a calculator. We teach it in our, well, when we had arithmetic class. And there's a way to compute, well, pi over 6, to compute pi without calculator. So you could do this all without a calculator, and you get 0.87475205. And so that's what it's approximately equal to. Any questions about that? Okay. So these are applications of doing approximations where you don't actually have to evaluate these. You can just somehow evaluate something else and get your answer. Now, of course, you will have to be able to evaluate this at a nice number. So we use the fact that we could figure out the square root of 100 to figure out the square root of 100.5. We use the fact that we could compute the cosine of 30 degrees to approximate the cosine of 29 degrees. Let me do problem number 30. Oh, so problem number 30. I'm sorry, problem number 38. So let's do problem number 38. When blood flows along a blood vessel, the flux F, the volume of blood per unit time that flows past a given point, is proportional to the fourth power of the radius r of the blood vessel. F is equal to K times r to the fourth. This is known as Poisson's law. Some French dude. We will show why it is true in section 8.4. A partially clogged artery can be expanded by an operation called angioplasty, in which a balloon-tipped catheter is inflated inside an artery in order to widen it and restore the normal blood flow. Show that the relative change in F is about 4 times the relative change in R. Okay, so let's do that. Oh, there's another question. How will a 5% increase in the radius affect the flow of blood? Okay, so we have following. No, it's an I. It's an I. The U's at the end. Oops. Law. So we have that force F is equal to some constant K times R to the 4th. So we want to look at the relative change. In F and the relative change in R. So the relative change in F is the change in F divided by F. The relative change in R is change in R divided by R. Okay, so we know our differential approximation. So we have a differential approximation. So our differential approximation is that, well, the change in F, the flow, is approximately dF, and the change in the radius of your artery is approximately dr. Okay, so now let's try to figure this out. So therefore, since F is equal to K R to the 4th, then dF is equal to 4 K R to the 3rd dr. So now let me divide both sides of my equation by F. So I have that this is equal to dF over F is equal to 4 KR cubed dr over F. But we know what F is. F is just KR to the 4th. So I have that dF over F, 4K R cubed dr over, well, f, which is kr to the 4. And so I have that df over f is equal to, well, k's cancel. 3 of the r's cancel. So you just have r in the denominator. And so this is equal to 4 times dr over r. Well, the change in f over f is approximately, well, the change in f is approximately df. And well, f is equal to f. But this is equal to, from the above here, 4 dr over r. But this is approximately equal to, well, the change in r is approximately dr. So this is approximately the change in r. And r is equal to r. And so that's what we wanted to show. We've shown that the relative change in f is 4 times the relative change in r. So the relative change in f in the flow, and so is 4 times, is approximately 4 times the relative change in the radius. And so that means that if you do this operation, then, if you change the radius of your, artery by a certain amount, r, then the flow will increase by a factor of 4 times that amount that you've done that relative change in. So if you change it by 25%, then you get a 100% increase in the flow. Oh, and so, well, so they actually ask us for, what if we do a 5% change? So when we do a 5% increase in the radius, what happens to the flow? Of course, that also means when you decrease the radius due to not eating correctly, bad exercise habits, the flow of your blood also decreases by 4 times the relative change. The relative change in your flow decreases by 4 times the relative change in your radius. So if I have from above that the relative change in the flow is 4 times the relative change in the radius, and we have that the radius is changing by positive 5%, then 4 times 5% is 20%. So a 5% increase in the radius will give an approximate increase in the blood flow by 20%. I can actually remember these from my physiology class. And so, yeah. Any questions about this?